This video, we're going to be talking about series, more importantly, infinite series. So I'm just going to go off and start with just what does a series actually look like. So an infinite series will have this form. It's the summation from n equals 1 to infinity of some sequence. Well, all you're really doing here is you're taking the sequence and you're adding up the terms accordingly. But there's a major problem with this. And the problem is we cannot add infinite terms. I mean, if you think about that, you would be doing this until the end of time. So instead, what we look at is the value of an infinite series is going to be defined by the limit of its partial sums. So let me write that out. The value of an infinite series is determined. Better yet, let's write it like this. Is defined in terms of the limit of partial sums. So what exactly does a partial sum look like? Well, a partial sum has this form right here. So it's still a summation. We're still starting at n equals 1. But in this case, we're only going to go to k. So we have our series right here. So it's a1 plus a2 plus a3. And we're going to go all the way up to some value a sub k. So let's consider this example here. We want to suppose oil is seeping into a lake such that 1,000 gallons enters the lake the first week. So week 1, oil seeps into a lake. And we know at week 1, 1,000 gallons did this. Now, week 2, the oil is still seeping. Oops. But in this case, it only seeps an additional 500 gallons. Now the third week, it's an additional 250 gallons. So what we know is oil is seeping into the lake, and each week it's basically being cut in half, and this is going to keep going. All right, so those little 3 dots represents. All right, so we assume this pattern continues forever. What can we say about the oil in the lake? All right, so let's think about this mathematically now. What we want to do is we want to look at we want to explore the amount of oil in the lake after K weeks. All right. So we're going to let SK denote the amount of oil in the lake measured after K weeks. So amount of oil all right. Excuse me. So week 1, we have 1,000 gallons. So I'm just going to put it as 1. So this is measured in thousands of gallons. Keep the math simple. So week 1, you have 1,000 gallons. Week 2, you have the initial plus half of that. All right. Week 3, you have what you had before plus a fourth. Week 4, and I think you can see where this is going now. Week 5. And so forth. All right. So we're starting to develop a pattern here. So what could we say then? Let me draw these dots a little bit nicer. What can we say about the amount of oil in the lake at any time? Well, it's going to be 1 plus a half plus a fourth plus an eighth plus a 16th. And it's going to go all the way down into 1 over 2K minus 1. And we can rewrite that in series notation as the summation of n equals 1 to k of 1/2 raised to the n minus 1 power. We can actually use this now to find the amount of oil by evaluating, just reading my notes here. So we're going to evaluate the limit as k goes to infinity of our series right here. So let's go ahead and let's see what happens. We know week 1, we have 1 or 1,000 gallons. Week 2, it's 1 plus a half. Well, that's going to be 3 over 2. Week 3, we have 7/4. Week 4, I'm not going to write it out. I'm just going to tell you what it equals. It's going to be 15/8. And then week 5, we get 31/16. And what ends up happening is this. If you were to take these, what we call partial sums, okay, along the horizontal axis, we're going to write out the weeks. On the vertical axis, it's going to be the amount of oil in the lake. You will notice that it kind of comes up and it's going to start flattening out a little bit. Now, if you were to actually calculate, if you were to calculate what these values are, you're going to find that our limit, as k goes to infinity, of the summation of n equals 1 to k of sk, which is the limit, as k goes to infinity, of our sequence, or our series, is equal to 2. So, as time goes to infinity, the amount of oil in the lake will be approximately 2,000 gallons. Now, this isn't exactly an ideal situation because it's oil in a lake, I understand. But this is what happens, and this is how we figure this stuff out. An infinite series is an expression of the form, the summation from n equals 1 to infinity of a sub n equals a1 plus a2 and continues on indefinitely. For each positive integer k, the sum denoted s sub k is equal to the summation from n equals 1 to k of a sub n, which is defined as a1 plus a2 all the way up to some finite number a sub k. Now, this is called the kth partial sum of the infinite series. The partial sums will form a sequence denoted S sub k with the brackets. I'm sorry, with the braces. Now, if the sequence converges, let me be more specific. If the sequence of partial sums converge, all right, then the series converges. And on the other side, they can both be divergent. Please note that series do not have to start at n equals 1. All right? We can allow them to start wherever we want, as long as it's a positive integer. But ideally, you want it to be like 0, 1, maybe 2, something like that. They're all different. All right? So, like, for example, we had this written earlier. This models our oil example. But we could also write it like this if we wanted to. Oh, horrible summation. You're going to have a lot of fun drawing these. Hopefully you get good at it. Hopefully you're better than me. So you could write it like this. Or, if you wanted to, you could start it at 5. I mean, they're all equivalent, okay? You can even change your variable up, all right? So, for example, and you'll actually learn a lot about this in DiffyQ, and you should have seen stuff like this in pre-calc. I don't know. That's why I'm going over this. But consider this example here. We have the summation from n equals 2 to infinity of 1 over n squared. We could introduce another variable, m equals n minus 1, so that n equals m plus 1. Now, what ends up happening here is no matter where you see the letter n, you're going to write m plus 1. So just watch for a second. You'll see what happens. So we get m plus 1 equals 2 for the start of the summation to infinity. Let me write this cleaner. There you go. Over m plus 1 to this quantity to the second power. And to simplify this, I'm going to subtract 1 from both sides. So I have a nice starting value at m equals 1 over 1 over the quantity m plus 1 to the second. So you actually do this a lot when you're trying to solve differential equations using series solutions. So the first thing I want to do, though, let's find some partial sums. So for example, we're going to look at the summation from n equals 1 to infinity of n over n plus 1. So for each of these, we're going to use the sequence of partial sums to determine whether the series converges or diverges. So for the first one here, when n equals 1, we get 1/2. When n equals 2, we get 1/2 plus 2/3. Remember, we're adding these terms up as they go. When n equals 3, we get 1/2 plus 2/3 plus 3/4. When n equals 4, we get 1/2 plus 2/3 plus 3/4 plus 4/5. Now, in each scenario, or notice that each term added is always going to be bigger than 1/2. So in other words, you started off with the first term 1/2. But then the second one is 1/2 plus 2/3, which is greater than 1/2 plus 1/2. Or 2 times a half, which equals 1. Now, with the third one, this is going to be greater than 1 half plus 1 half plus 1 half, which is 3 over 2. And this is going to be greater than 1 half plus a half plus a half plus a half, which is 4 times a half, or 2. And what we can see here is when we add up these terms, they are just progressively getting larger and larger and larger. 1 half, 1, 3 halves, 2. So, from this pattern, we can see that the partial sums of S is always going to be greater than K times 1 half for every integer K. Thus, since our partial sums, diverge, our series, which I'm going to write right here, also diverges. And that's basically it. That's all you got to worry about. It's a little bit confusing at first, okay? But the idea is it should start to converge to a value. And if you just kept doing this, we'll never ever converge. In fact, you could even plot this, and you will notice that it just keeps growing and growing and growing. Let's look at another example here. And this one will converge. I'll show you what a convergent one looks like. So we're still going to find the partial sums to determine whether or not this converges. And we're just going to switch it up just a little bit. So notice this problem here looks very similar to the one we just looked at. However, I'm going to tell you this converges. Now, let me show you how. First thing we're going to do is we're going to write out these partial sums. So for the first, you get 1 half. For the second partial sum, if you just do the math real quick, you get 2/3. For the third partial sum, you end up with 1 half plus a 1/6 plus a 1/12 equals 3/4. Now, before we move on any further, I want us to highlight something. First, notice, and I'm going to kind of make this explicit here. Every time we add something on to our next partial sum, it's smaller than the previous. All right? Like it's smaller than the previous. That was not happening here. Every single time we added something, it was larger than the previous. All right? So you got to be like, this is how we're thinking about this. All right? Is if we're diverging, that means as I add something on, I'm adding something bigger. In our second example here, when we add something on, we're just adding a very little bit small amount. We're not adding a lot. So with our fourth partial sum, we end up getting the following. Sorry, I'm just writing it out real quick I think you can follow along with me now. Notice here, we're adding 1/20th. And you could see, like I said, let me highlight now our partial sums. Here are the partial sums. 1/2, 2/3, 3/4, 4/5, and we'll do one more. We'll keep with it. Notice here we just added 1/30th, but this ends up equaling 5/6. Oops, didn't hit the marker. There we go. So when we look at the terms in our sequence here, we have 1/2, 2/3, 3/4, 4/5, 5/6. So it looks like this is going to converge to 1. The pattern that we end up getting, we can define the sequence of our kth partial sum to be k over k plus 1, where k is greater than or equal to 1. So because this converges to 1, so because our partial sums converge to 1, our summation from n equals 1 of 1 over n times the quantity n plus 1 equals 1. The harmonic series is defined as the summation of n equals 1 to infinity of 1 over n, which is 1 plus 1/2 plus 1/3 plus 1/4. And this series, although it looks like it's going to converge, it actually diverges. Okay? It diverges. So let's see why for a second, okay? Our first partial sum is going to be 1. The next partial sum is 1 plus 1/2. The next partial sum is 1 plus 1/2 plus 1/3. So although the next term we add is smaller than the previous, it's not small enough. All right? It's not small enough. What we say is it's not getting small quick enough. All right? So in our fourth partial sum, let's examine this. So notice that for the last two terms in our fourth partial sum, for these two terms right here, 1/3 plus 1/4, that is greater than 1/4 plus 1/4. Therefore, we're going to conclude that the fourth partial sum is greater than 1 plus 1/2 plus 1/4 plus 1/4, which is equal to 1 plus 1/2 plus 1/2, which is equal to, oops, ran out of space, which is equal to 1 plus 2 times 1/2, or 1 plus 1, which equals 2. So what ends up happening is this is not getting smaller and smaller and smaller. It's actually getting larger and larger and larger. All right? So if I asked you to memorize anything, it's know that the harmonic series diverges. Okay, and here are the algebraic properties of convergent series. So basically, how you want to look at this is you have two series, infinite series, a sub n, b sub n, and they're both convergent. So if they're both convergent, then the following algebraic properties hold. You can distribute the series if you want. That's what we get down here. You can take a constant and move it out front. That's what we get right here. And then part 2 is just an extension of part 1. It's just add or subtract. That's it.